This is the last topic for this semester, sampling and sampling distributions. In this lecture, we will learn describe a simple random sample and why sampling is important, explain the difference between descriptive and inferential statistics, define the concepts of sampling distribution, determine the mean and standard deviation for the sampling distribution of sample mean, and describe the central limit theorem and its importance. Two parts of statistics, descriptive statistics and inferential statistics. In descriptive statistics, we talk about collecting by survey, presenting by graph, and describing data. In inferential statistics, we will draw conclusion and make a decision about the population, the large set, based on sample data, small set. That is, in inferential statistics, we will take information from small set, which is the subset of large set, and using this information, we will draw some conclusions about the large set. Okay, now let's start learning what is population and sample. Definition of population. Population is the set of all items or individuals about which you want to draw a conclusion. If your topic about something, then all items or individuals about this topic you must consider as a population. Like in these examples. Suppose your research topic, all parts produced today, yes, your research topic. Then all parts produced today you must consider as population. If your research about students at UFAS, all students at UFAS you must consider as population. If your topic about the letters in English alphabet, then all letters in English alphabet you must consider as population. Population, as always, a big set. It's impossible to get the direct information about population because it's too huge and it's not possible to take information from it. That is why, for this reason, we use sample. Sample is a subset of population, consists of small number of items or individuals, and it's easy to get information about it. Here is some examples about sample. If all parts produced today in a factory you consider as population, then sample will be a few parts selected for descriptive testing. All students at UFAS, this is population. Then some students who attend to survey you may consider as sample. All letters in English alphabet, then letters in the word, this word, you can consider as sample. Population and sample, the selection of population and sample depend on your research topic and how you want to analyze it. Okay, that's why it can be different. For some person, for example, all students at UFAS can be population, but the sample can be students at L0, for example, or students at L2, or for example, chemical engineering students just. Here it's written some students who attend survey. This is also possible. Okay, sample and population, they can be changed depend on situation. Okay, here is visual representation of the last example. If population represent the letters in English alphabet, all letters you see here we consider as population. Then sample is some of them selected for analysis. Let's now try to understand why we use sample. First, sample less time consuming than analyzing large set, less costly than analyzing the large set. It is possible to obtain statistical results of sufficiently high precision based on sample. It means that instead of population, you may use sample, and it helps you to time consuming, not to waste a lot of money, and get the result with high precision based on sample. In lecture 5, we talk about descriptive statistics. I told you that in descriptive statistics, our work is just to collect and present the collected information by using the graph, by using the numerical methods. And now let's learn the second part of statistics, inferential statistics. Making the statement about the population by examining the sample result. In inferential statistics, we will use exactly sample. And based on sample, we will draw some conclusions about the population. Here, how we will do this. Population, the values about the population called parameters. They are unknown because it's a big set and you cannot calculate the characteristic of this large set. That's why parameters always unknown, but can be estimated from the sample result. And the sample is so small and you select it in order to analyze it. That's why it's always simple to analyze, and sample data always known. And you take the sample, calculate some numerical values from this sample, and based on this result, you will draw the conclusion about the population. This is the general what in inferential statistics we will do. Okay, it's a general thing what we will do in inferential statistics. In order to find out the results or conclusions about the population, we will use samples selected from it, calculate some numbers from the sample, and based on this result, we will draw some conclusion about the population. Sampling distribution. What is sampling distribution? Sampling distribution is a distribution of all possible values of statistic for a given sample selected from a population. What does it mean, students? Suppose that you have a population. From this population, you may select sample with size 5, let's say. There are many samples you may select from the population with size 5, yes? You may calculate some measure from this sample. For example, mean. You may calculate the mean for all possible samples selected from population with size 5. The collection of all numbers, in our current case, the collection of all sample means, we consider as sampling distribution. Okay? From the population, you select all possible samples with size 5 I say as example. Then you calculate the mean for all these samples. Then the collection of all sample means represent sampling distribution. Okay, just this thing. There are 3 sample distributions: the distribution of sample mean, distribution of sample proportion, distribution of sample variance. In this case, we just calculate the mean of all selected samples, proportion of all selected samples, and here variance of all selected samples. In our current lecture, we just cover this part, sampling distribution of sample mean. Now we are going to construct sampling distribution of sample mean. Suppose that we have a population just consists of 4 persons. Actually, it's not correct. Population is always big set. This is just for explanation, okay? Just for explanation, we take population which consists of just 4 elements. Let's say we have 4 peoples, A, B, C, D. Population size equal to 4, of course. Let random variable x represent the age of these peoples. Values of x for these peoples are 18, 20, 22, and 24 years. Now we will calculate the measures of population, and after measures of sampling distribution, and then we will compare them. Let's start finding the measures of population. First, mean. As you see, population mean we sign by mu, Greek letter mu, equal to sum of the ages of these 4 peoples divided by their number. It's 21. Sigma, which represent population standard deviation, and the difference between sample standard deviation and population standard deviation is denominator. In denominator of population we have n here, but for sample we have here n minus 1. Calculated using this formula, it gives us 2.236. These 2 measures we need for population. And now probability distribution of population. Because we have 4 peoples and their age different, but there is no any difference between these peoples. I want to say there is no difference. Select the person here. You may select each one. So you must consider the probability of for selecting each one as equal. That is why probability of selecting each 1 over 4, 0.25. Now we start finding the characteristic of sampling distribution. In order to make the calculations easier and understandable, we will select sample with size 2 from this population. And the sample selection we consider here with replacement. It means that if you select one person, you return it, and it's possible that you may take this person again. That's how you select the sample in sampling distribution. Okay, so we consider 2 observations for the sample size 2. First observation is possible that you may select as a first person to make 2 persons in the sample. First 18, 20, and 22, 24. Second observation, same pupils. That is why we can have here as a sample 18, 18. Why this occur? Because it's possible that you may select the first person with age 18. You return back this person and you may select this same person again. That is why 18, 18 is possible as a sample with size 2. Then 18, 20, 18, 22, 18, 24, and 24, 24. As you see, from the population of size 4, we may select 16 samples with replacement. Okay? Now, you may calculate the mean of all samples. For the first sample, in order to calculate the mean, you need to add these two numbers and divide by their number. How many numbers we have? Just 2. 18 plus 18 is 18. 18 plus 20 is 38. 38 divided by 2 is 19. 40 divided by 2, 20. And 42 divided by 2 is 21. And at the end, you see here 24, 24. The average of these two numbers is 24. So we obtain the mean of all possible samples with size 2. Now we are going to draw this probability distribution of all these sample means. Here we have 16 sample means. We have 118, 219, 320, 421, 322, 223 and 124. We draw the graph. On the horizontal axis, we will show the mean of this sample means, the number of the samples means 18, 20, 21, 22, 23 and 24. And in vertical axis, we will show, as always, the probability in order to make the probability distribution. The probability of sample mean, our variable we consider sample mean, being 18 is 1 over 16. Probability sample mean being 19 is 2 over 16, that is 1 over 8. Yes. Probability of sample mean being 20 is 3 over 16, something here. Probability of being sample mean being 21, 4 over 16. 4 over 16 is, if you simplify it, 1 over 4, 0.25, you see. And again, it starts decreasing. For 22, it's 3 over 16. For 23, it's 2 over 16. And for 24, it's 1 over 16. You see, sample mean start increasing. And then after the maximum, it start decreasing. You see, we take here sample mean 2. And its graph look like a bell. It's symmetrical. Which distribution it's remember to you? Which distribution? It's something which is going to close to normal distribution if you take sample size not 2 but more than 30. Okay, but it's impossible to do because you see samples with replacement we do here. That's why it's impossible to show. It's possible to do, but it's impossible to show you this thing. You see, even we select the sample size 2, our distribution of sample means behave it like a normal distribution. Let's now calculate the measures of sample means. We have 16 samples. You may find its mean by adding and dividing by number of values. You add them and divide by 16, you get 21. As you see here, it's again equal to population mean. And you calculate the standard deviation of sample mean by using the standard deviation formula for population by this formula, and you obtain 1.58. Let's now compare population and sampling distribution. Population with size 4, calculated mean 21, standard deviation 2.236, and distribution even. Sample sample mean distribution. We select all possible samples with size 2. We calculate the mean of all 16 samples as 21 and standard deviation of all sample means as 1.58, and then we draw the graph of sampling distribution. As you see, previously the graph was like a uniform distribution, probability for each number same, but when we select the sample and make the sampling distribution, the graph look like a normal distribution. Using this property, we will calculate the probabilities about the sample mean. Using the property that after the sum number, sampling distribution behaved exactly like a normal distribution. As you see, population mean here 21 and sample mean 21. This is always correct. And there is also a relation between population standard deviation and the standard deviation of sample means. There is a relation between these two numbers. We are going to show it in the next slide. Standard deviation of all sample means called standard error, and that is the relation between standard deviation of sample means and population standard deviation. Formula is very simple formula. Just population standard deviation divided by square root of n equal to standard deviation of sample means. And here you see that if we increase the sample size, population standard deviation constant, if population standard deviation constant, then sampling distribution, the standard deviation of sampling distribution decreases as n increases. If sample size is greater than 5% of population size, we can use finite population correction. What is it? If the sampling without replacement and sample size is large relative to population, that is n greater than 5% of n, then variance of sample means we calculate using this formula, and standard deviation of sample means we calculate using this formula. Here this coefficient and this coefficient, they make your calculations more accurate. This one you apply when the sample size more than 5% of population size. It gives you more accurate answer for probability and for everything. So if n is not small compared to the population size, in order to calculate the z-value, we can use this formula, more accurate formula for z-value. Okay, now we are going to explain the second case when the population is not normal. For this case, we need to remember something from the previous slides. As we told before, as n increases, standard deviation of sample means decreases, and the form of the graph changes when n increases, which represent the sample size. Central limit theorem say to us that as the sample size gets large enough, the sampling distribution becomes almost normal regardless of the shape of population. Central limit theorem said that if you increase the sample size, then after some number of sample size, the distribution of sample mean gets close to normal distribution. So, if population is not normal, we can apply central limit theorem. It's said that even if population is not normal, sample means from population will be approximately normal as long as the sample size is large enough, and you may apply again these formulas. Okay, now it's time to learn that number. How large is large enough? What is the sample size we should take in order to get the sampling distribution behaving it like a normal distribution? This number is 30. For most distributions, when n sample size more than or equal to 30, it will give us sampling distribution that is nearly normal. Let's now consider example about sampling distribution. How to calculate the probability of sampling distribution. Suppose we have a population with mean 8 and standard deviation 3. Suppose a random sample of size 36 is selected from this population. Then, what is the probability that the sample mean is between 7.75 and 8.25? As you see, students, there is no anything about the distribution of population mentioned here. There is no anything about the population distribution. So you cannot say that population is normally distributed. It's not given to us. But because of the sample size more than 30, we can say that it doesn't matter for us how the population distributed. Sampling distribution almost normal. We can take the sampling distribution normal because of central limit theorem, because sample size more than or equal to 30, because of 36. So we will apply standard normal distribution to calculate this probability. Solution. Even if the population is not normally distributed, the central limit theorem can be used. So the sampling distribution of sample mean is approximately normal, with mean of sample means 8, which is equal to population mean, and standard deviation of sample means equal to 0.5, calculated using this formula. Probability of sample mean being between these two numbers equal to probability of z being between these two numbers. As you see here, we transfer this sample mean to standardized normal distribution using the formula, and this 8.25 similarly to this. So we obtain in the left and right side of z negative 0.5 and positive 0.5, which you can easily find out from a standard normal distribution table. Let's find out it. Okay, now let's calculate probability z less than 0.5. It's 0.6915. That's the number here, left side area, 0.6915. And here, probability of z less than negative 0.5, it's 0.3085. So, probability of z less than this is 0.3085. So, you have this area, you have this area. If you subtract from this area, you will find out probability of z being between these two numbers. and we get at the end probability of z being between these two numbers as 0.3830. So let's make a conclusion. Before we have a population, there is no any information about it except mean and standard deviation. So we don't know how it's distributed. Population distribution unknown. We take from this population sample with size 36 all possible samples and create the distribution of sample means. Using the central limit theorem, we can say that it's normally distributed. And the probability, if we want to find sample mean being between these two numbers, you may calculate transferring this to standardized normal distribution by the formulas. You obtain here negative 0.5 and positive 0.5. I know that the graphs look like the same, but actually they are not same. And this area, green area, equal to this pink area. The probability of x being between these two numbers equal to probability of z being between these two numbers, which is 3830. That's all. We finished this topic. We understand how to find out probabilities about sample means using population mean and population standard deviation.